Hello, thanks for watching. This is Balancing Act Day 1. Although largely we are wrapping up Change is a Constant, and you'll get some quick reminders before you take your assessment on Change is a Constant. And then I will try to walk you through how you're going to get started with Balancing Act, the nitrogen cycle, by using a pair deck. All right, so finishing up Change is a Constant. Excuse me, this is our warm up. What is one reason that scientists use graphs? Well, you know that scientists are going to use graphs to show relationships in an ecosystem or to show change over time in an ecosystem. Of course, we use graphs in other ways as well, but because we are thinking about ecosystems with change as a constant, we just want to focus on how we might use graphs in our current unit. So number 2 here, we're going to look at a predator-prey graph. This is pretty typical of any predator and prey situation. And you'll notice anytime you get a graph, you want to look at the things you can see. So we know that this y-axis is talking about population. We know this x-axis along here is talking about time. And I can see that this line, this blue line here, is the prey. So this is measuring prey over time. And the red line is measuring the number of predators available. It's pretty typical so that we have prey, that's the animal that's going to be eaten. As the number of prey increases, it actually allows the number of predators to increase because there's more food available for them. So the prey are increasing here, and you can see that the predators are increasing. But as the predators increase a fair bit, suddenly there's going to be enough predators that it will reduce the number of prey we have because they're eating them all, right? So we suddenly have a much smaller amount of prey available because we have more predators. As soon as we have fewer prey available, our predator numbers are going to go back down. And it's a cycle. It keeps going on like that. As the prey number goes up, the predator is lagging behind, and it'll go up a little bit too. As the prey numbers fall down, and they are falling down because there's more predators, as the prey numbers fall down, the predators will fall down first, and then the prey will go back up, and so the predators can go back up. Pretty typical. All right. So these are some review questions from earlier in the year. Think about finishing these phrases. Surfaces like roads and sidewalks are called blank because they don't blank. So hopefully this picture is going to remind you of the types of words we're looking for. Roads and sidewalks are impermeable. They don't allow water to soak in, and so that water is just going to run right off of them, oftentimes into a storm drain like in this image. The type of surface increases the amount of surface runoff, which flows into a storm drain, which leads to the nearest waterway. Okay, so an impermeable surface increases the amount of surface runoff that's going to go into these storm drains because it can't soak into the ground. It has to go somewhere. It's going to go into the storm drains. As that runoff flows over the surface, it can pick up contaminants. Okay, and there's lots of contaminants. So if you're thinking about words that you might fill in here, you're probably right. Our examples that we have written are car oil and road salt, but it's also going to pick up trash, animal waste. It's going to pick up little bits of fertilizer. So lots and lots of things that are somehow on these impermeable surfaces that get caught up in the water. All right. After a heavy rainstorm, the waters of the Chesapeake Bay could become more polluted because we have water coming along, running off these impermeable surfaces and collecting all kinds of contaminants. Once it goes into those storm drains, it's going directly into the waterways. And so any pollution that's in and along these roadways and sidewalks is going to end up in our Chesapeake Bay, which is ultimately where all of our water goes. All right, so if we want to think about change as a constant and we want to think about phrases and words that we are using in this unit, We want to know, what would the disruption be? What's happening? Because we are thinking about disruptions to our ecosystems. If you're thinking about Isle Royal, we have disruptions when we have no ice bridge, and so we can't have more wolves come over, or we might have a disruption if we have a particularly bad winter and we don't have enough moose surviving. So in this case, we're thinking about the Chesapeake Bay and some pollution, right? So what's the disruption? We have pollutants entering the bay. What's happening? Pollutants are entering the bay. That's going to be a short-term thing. It's happening right away, right? It's happening as that water is going through those storm drains. And definitely that is largely man-made. Okay, how could this change or impact the populations in the Chesapeake Bay ecosystem? Whoops, sorry, I thought I was going to have answers. So those pollutants, depending on what they are, they absolutely can cause damage to fish and plants. Or if it's some sort of a fertilizer, it actually might cause some of the algae to grow a lot. And if the algae is growing a lot, it might actually choke out some of those lower level plants that are in the water, because the lower level plants no longer get the sun they need. And if they are chemical pollutants, they might make fish and oysters and things like that sick. So lots of things could happen. All right, so I have a video for carrying capacity that I'm going to show. And if you already watched this video, or if you feel pretty comfortable with carrying capacity, you can fast forward through this.
Welcome to Moo Moo Math and Science. In this video, I'd like to talk about carrying capacity of an environment. The maximum number of individuals in a species that an environment can support for the long term is the carrying capacity. Carrying capacity is limited by the energy, water, oxygen, and space, which are all limiting factors. As a population nears the carrying capacity, resources become limited. And if a population exceeds the carrying capacity, deaths begin to outnumber births. Let's take a look at the fish family that live in the fishbowl. Life is plentiful. There's plenty of space. There's food to eat. There's energy from the sun. And they're able to reproduce. However, as they reproduce, resources begin to become limited. They're limited by space and the amount of food. However, they're still able to reproduce. Eventually, there become so many fish that some of the fish begin to die off because there's not food to eat and the water is limited. They have reached the carrying capacity, and deaths will outnumber births until it gets back in balance. So there we go. The largest population that an environment can support is known as the carrying capacity. Thanks for watching, and Moo Moo Math uploads a new math and science video every day.
Okay, so at the end of last class, or partly during last class, you started working on a rabbit population gizmos, and that you can access through Schoology. You were filling in answers on a worksheet that I also posted in Schoology. So you were not answering the questions that are online with that gizmos. You were answering questions on paper. So if we think quickly about our gizmos, we noticed when we looked at the population over time, this is the population of rabbits, we can see that it goes up and down, right? And you can see that there is definitely a pattern. And when you looked more closely, you could see it changed with the seasons. So I'm also going to ask you to look at, this is years down here. So we started maybe at, 50 rabbits or something like this at the year 0. And you can see that maybe year 1, we jumped up to 150, year 2, year 3. It's around year 4 that we start to hit our carrying capacity. We're pretty balanced right here at our carrying capacity. And if I had to estimate, if I had to guess what the carrying capacity is, right here, it's kind of in the middle of that up and down situation. I'm going to keep going left, and I would say probably the carrying capacity is about 400 rabbits. That seems to be where our population numbers are going, bouncing around up and down over 400. All right, so we notice about this rabbit population over 10 years that in the beginning it increased, maybe for the first 4 years, but then it was pretty steady. Okay, that is the carrying capacity again. That's the maximum number of individuals of a particular species that an environment can support. All right, and why is that? Well, when we look at it, we can see that it increases and decreases around the same time each year, and it has to do with the seasons. We can see that it was pretty low numbers in the winter and pretty high numbers in the spring, and it kept that pattern going. Okay, so here's our pattern, still going. The main cause of that population going up and down is that rabbits reproduce during the seasons when there is more food available. So there's going to be more food available in the spring and less food available in the winter. When resources are harder to find during the wintertime, for example, we also have more rabbits dying. All right, so is this short-term or long-term? We're going to say short-term. Remember, things with seasons, things that are changing with the seasons, those are short-term changes. Those individuals are born and they die over the course of a few months. Seasons are over months, right? Okay, so if the rabbits had less space to roam, would our carrying capacity be higher or lower? You were doing changes, you were making changes on your gizmos so you could see what was happening. So when we have ample land, ample means enough or even plenty, then that was our first carrying capacity that we could see. We were right around 400 if we kind of guessed a number of rabbits that was the average amount. That's when we were having plenty of land. So if we think about it, if we have less space for these rabbits to roam and find food, I bet there are going to be fewer rabbits available to us. And that is what we had. When you changed in the gizmos the amount of land that was available to, say, little land, you still have the up and down cycles. You can still see some changes from winter to spring, but we are much lower average. This average is closer to 100. Right here would be 100, 200, 300, 400, right? So it's much lower, but we can still see those same patterns. Oops, I forgot I had those fancy lines. Okay, so we can call this a density-dependent limiting factor. So remember, limiting factors are things that affect how many of a particular species, how many organisms we might have of a particular species. So density-dependent limiting factor affects a population when the density, the number of individuals in that spot, reaches a certain level. So as long as we were lower numbers down here, we could grow and have more rabbits. But density-dependent limiting factor means that this number really depends on the density, and it's going to be a pretty consistent number. All right, how else do you think seasons impact ecosystems? Not just rabbits, but ecosystems in general. So we have fall, we have migrating birds, we have a big healthy looking squirrel there. So we have some animals that are going to hibernate. We have some animals that are going to migrate because of the seasons. And we also know that long-term, some animals and plants end up with adaptations that make them more suitable to live in their biomes. And different food sources come about depending on the time of year. So that is an effect of seasons because we have different plants and things growing, different animals available at different times of the year. All right, so here's another video. This one's on limiting factor. And again, if you've already watched this, you can fast forward through it. You can skip over this video. I'm going to show it anyway so that if you haven't seen it, you can see it now.
Welcome to Moo Moo Math and Science. In this video, I'd like to talk about limiting factors. Any abiotic factor or biotic factor that restricts the number Welcome to Moo Math and Science. In this video, I'd like to talk about limiting factors. Any abiotic factor or biotic factor that restricts the number or reproduction of organisms in an ecosystem is called a limiting factor. Take this ecosystem found in the fishbowl. The limiting factors could be the size of the bowl, the amount of water, or the temperature, and any of these can limit the number of fish that can survive in the fishbowl. Limiting factors can be dependent limiting factors and independent limiting factors. Dependent limiting factors depend on the number of organisms. For example, the amount of food available for each organism depends on the number of organisms in this ecosystem. And independent limiting factors does not depend on the number of organisms. For example, the amount of rainfall does not depend on the number of organisms. You also have density-dependent limiting factors, and it is a limiting factor that depends on population size. For example, these could include competition, predation, parasitism, and disease. Let's look at a list of abiotic limiting factors. This could include sunlight, climate, temperature, water, space, soil chemistry, fire, and natural disasters. And a list of biotic limiting factors include the number of plants, number of animals, amount of competition, number of decomposers, number of parasites, and disease-causing agents. So there we go, limiting factors, biotic and abiotic factors that limit the size, number, and reproduction of organisms in an ecosystem.
And of course, I'm sorry for covering up our little Moo Math guy's face a little bit while we were watching that. Whoopsie daisy. But you were still able to hear what he was saying about limiting factors. All right, so at this point in class, students who were in the building would have turned in their gizmo and gotten ready for the test. The test was informative, and if you were absent on this day and you didn't take your test, of course you want to come and figure out when you can make it up. So thanks very much for watching this part. Now realize that people would have taken their test on change as a constant, and I'm going to walk you through what would have happened with the Pear Deck in a second video. So you'll look for that second video to see what happens with our balancing act Pear Deck.